Hello. We made a temperature string.
We did.
I'm Jaden.
I'm Sam.
Emily.
Her name's spelled wrong.
What did you do?
Well, it was, but we fixed it.
Oh.
So for measuring temperature, the basic sensor that we use are these TMP 36 sensors. They're very small, as you can see, and they cost about $1.50 each. The specs say that they can measure from -40 to 125 Celsius within an accuracy of 2 degrees either way. And they provide an analog output, so just like the last group, we had to use a converter in order to get that into a digital signal.
And the $1.60 each is a really nice cost because in case you're given 15 and you want to have a sensor with 4 of them and you break 11 of them, you feel like you haven't wasted too much money. Yeah, so what's it actually do? Multiple sensors connect to one data logger, which allows simultaneous temperature measurements. The reason that that's sort of challenging is just wiring it mainly so that you've got no contact between the different conductors of these different sensors, as well as having to, every time you have a data line, you have to extend that through. So if you've got 4 data lines, 4 sensors, you need 4 data lines going through, which means at the top of that you've got 4 data lines going through some little hole or something in terms of our architecture, which just adds kind of clutter. But it's the length of that data line that's kind of the limiting factor on doing this, because as you add more and more sensors, you add more and more data lines. What it does do is it allows for continuous measurements along a temperature gradient as that gradient progresses. So, you might say, okay, we want to know how deep it is at 5 feet and then 10 feet and 20 feet. But that's pretty easy to do with one temperature sensor. But if you know that there is some heat flux and there's going to be a gradient that's progressing and you want to observe that gradient progressing at the same time using the same sensor array, that's what this is going to be able to do. The fishing wire that we're using allows for high load on the apparatus. You see right there, none of the wires is supporting that. And it is waterproofed to allow for use underwater in high humidity environments like volcanic vents or in ice, pretty much any place you want to put it where it's not necessarily getting crazy hot, so it's going to melt the apparatus. You can, because it's epoxy to hell, and none of the actual connections are, exposed.
Before we move further,
Yeah.
the building process of it was a bit of a fun thing.
You turned it off.
Is the next step? What did I put this one up? Is the next the image?
Well, yeah, but how do we help?
There was just that loose connection.
There we go.
Yeah, right.
Okay. It's the next slide, right? So we have.
Yeah, but we got to get this connected.
When you mess with it, it'll come back on.
There we go. So we are willing to advertise it as bomb-proof.
Okay, so this was our original plan of what we wanted to do, and we were like, we can connect all of these and make all of these separately and then put it together. And this is kind of what connecting all of these ended up looking like, which if you look at the size of the things that were machined, exactly the size we wanted them to, that doesn't really fit in there anymore.
And really quick, the reason we put the sensors inside these metal pucks is to allow the metal to couple with whatever hot or cold thing we're trying to measure. And that way the sensor is measuring directly the temperature on the puck rather than trying to measure the temperature on the small area that the sensor has.
Yeah. So, do you guys want to walk through how it actually got connected, or?
Yeah.
Let's do that.
Okay. So on the previous slide, we saw that these little sensors are analog and they have the ground, the power, and the data line. So to connect all of those to something like your laptop, you're going to be able to collect your data. We have this little schematic to help us understand what's going on and how many wires we actually need. So the first thing that we did was to connect the ground. Purple was ground for us today. And for that, we were able to use one long continuous wire, and continuous by the means that there were like very many junctions that we had to epoxy to make them waterproof because we kept using shorter wires than we needed, and we needed to like strip them for everything there. But turns out then we had the open window stripping in epoxy to waterproof even more. So we actually did things good. Okay. Then the next one that we did was the power line. So that is again able to be continuous throughout the entire thing. And then comes the fun of the data line and why this is kind of a little wire mess. So we have the first data line that starts from this sensor over here, goes all the way to the that. Then we have another one, and another one, and another one. So you need a data line for each of these sensors because that's the output that you are going to read with your laptop. So that's how this came to be.
And then we plug it into a computer operated by Emily. So, Emily, you want to take the calibration?
Where are the pictures?
They're going to be there.
Okay. Can we have a picture?
Go through the
Okay.
calibrations first.
Okay. So to calibrate the sensor, we put it in the, is it called an oven if it goes cold?
It's a heat control.
Heat control.
Temperature control.
Heat control chamber. Temperature control chamber. And we put there. We had it hooked from the little hole that there's in there to our computer so we could see the live change in voltage in our sensors as we were varying the temperature on the computer. And that raw data looks like, yeah, it looks like this. So here you can see all of the steps and temperature that we did. For the purpose of what we wanted to do, we wanted to test our instrument in ice water as well as under a car. So we kind of estimated what those extreme temperature would be like. So we tested it at -4 degrees as a minimum temperature, as well as 40 degrees Celsius, everyone's Celsius, superior unit. For the, yeah, and then each of these steps are going from -4 degrees, then to 0 degrees, 10 degrees, and then finally 40 degrees. And when we thought it was equilibrated enough, we would just go up one more step. So that gave us 4 data points to try to calibrate our instrument relating voltage to temperature. And what we found is that we did different calibration for each of the sensors. And if we zoom in on our -4 degrees right here, the circles are the calibration given by the data sheet of the sensors. And the triangles is the data that we got. So what we can see is that for the same voltage, we predict a lower temperature than what the sensor does. But also notice that the gap in data is smaller than the error of the sensor that was given by the data sheet. So we were pretty happy with that. And then we also see that for each sensor at the same temperature, they are outputting different voltage, hence enhancing the fact that we should probably use a different calibration for all of them so that they are giving constant temperature. And then we also did it for 40 degrees Celsius, where we had the opposite problem, where our data was overestimating the temperature slightly, but still by less than a degree Celsius. So we were pretty happy with that. So then the calibration lines that we use for our tests are linear fits, which is very easy to do. And yeah, and those are the equations you saw at the beginning. Here. And they're slightly different for each of the sensors. This is the one given by the spec sheet. Ours are just a little more decimal places.
So for a dry test, we put it underneath my car to see how it was going to change as I turned it on. This is my car. But imagine instead of being on the concrete, we parked it on some grass so that you weren't getting the effect of the hot concrete, but rather the grass. And then we put one sensor there sort of further underneath the car, one sensor there at the edge of the car, one sensor on the grass, sort of just in front of the car, and then one sensor a little further away. Then we turn the car on, and then we started looking at our peaks. So it started pretty hot, and part of the reason that it started as hot is it was hot out yesterday. So you can see where we've turned the car on is going to be around maybe 11 minutes.
Here.
Yeah. But then you can also see that at a certain point we saw that the first sensors we had were getting a little too hot, those two that were out on the grass. So we put some cardboard over them to cool them down. And then you can see those starting to cool down. And progressively, the sensor that was furthest underneath the car heated up the most, getting up pretty hot, around 55 degrees, which, given that we were recommended not to test the sensor over 60 degrees, was sketchy. But continued to work well. And then you can see pretty easily where we turned the car off. And yeah, I'm kind of curious about, and I don't think we spent much time thinking about this, whether or not that peak in temperature we see there is just about the sun or the clouds, or whether or not that was actually about the car turning on at all, given that those were out on the grass. I don't have a great answer on that. We also don't really know what's going on with that little
It
bump up there.
immediately drops when we put the shade on.
I know it immediately drops when we put the shade on, but it's still, you know, a little elevated and it's moving a little slower. I think you're probably right. That's my guess, but I'd be curious about doing it again and like keeping the shade on it.
Oh.
Yeah. So that was our dry test. Jaden wanted to note that if we were doing Ferris Bueller, he was slow. Jaden, you want to take the wet test?
Yeah, so we did the dry test first because we wanted to get data in case our bomb proofing was insufficient. So then we did a wet test where the plan was to put the one end in ice and have the other sensors in water, and then we would see as the ice melted and that cold water maybe flowed towards the other ones. And and so we ended up having a little trouble due to mainly time and forgetting that ice floats. We had a little trouble keeping the sensor in ice. And
Jaden and I are both glaciologists.
So yeah, that's a slight oversight. Another issue that we had was we were running this off a laptop, and when the laptop went to sleep, it stopped collecting data. So we have 15 minutes of data, and what you can see here, is this is when we turned it on. We hadn't put the sensor in the ice yet, and this is us messing with the ice and trying to get the sensor to stay with the ice without it floating away. And it did work fairly well. As you can see, the sensor equilibrated with the ice and got down almost to freezing, while the other ones were in the relatively warm water that had been out in the sun all day. So one was in ice and it was colder, and it ran and was waterproof. So that was what we learned here.
And we left it there for 2 hours, maybe, to realize we had 13 minutes of data, and we're like, oh no.
We wanted to know
Was it not waterproof
what
after
happened.
13 minutes?
Did
But no,
it-
it still works.
And we tested it. It did, which
Yeah.
means questions, y'all?
What is this?
When I was in middle school, I was in a presentation and somebody put a dolphin at the end of the presentation, and since then I've included a dolphin in every presentation I've ever made.
Okay.
What's up, Jackie?
I have 2 questions. Okay, so on your last slide, why do you think that the sensors that were all in the same water, there's like an offset of a couple degrees between the green one and like the pink and the red?
Yeah, let me go back and check something really quickly. So that's sensor 4 is the blue, and then do we know which sensor
Well,
is according to which
the,
color?
The grainy
Yeah.
is the one that is right here close to the rock jack.
Yeah.
Because we needed this part to be out of the water. It was a lot closer to the surface of the water, so it wasn't like surrounded by as much like cold
Yeah.
water. And so that's why that one is more different, and then the other ones are basically within a degree of each other.
And then I was gonna ask, your car, like you said, you shielded it with cardboard, and then the car was shielding. So do you think that the car itself versus the cardboard might have affected your temperature measurements?
Could have. I think just given the general position of the sun, where you see the shadows coming, that car's probably not actually shadowing those first two temperature sensors. Obviously, there is some shadowing, so you're not getting the impact of the sun on those sensors that are underneath the car, which is why actually before it turns on, you see that the sensors that are underneath the car are actually at a lower temperature.
Yeah.
Because
were you trying to measure the concrete or like the
we were so all the sensors were on the grass. We were trying to measure how the sensors heated up differently as we turned the car on.
Gotcha.
I actually wanted to try and put them in the engine, but it occurred to us that we might really, mess some things up.
Yeah.
Yeah, because you don't know the temperature limits of fishing line.
Mm-hmm.
I don't think it's one of their priorities. So we didn't want to test that in his engine because he still has to drive back.
Yeah. Any other questions?
Do you have any guess from your testing in here or the testing that you presented and what the time constant is on if you take one of those sensors
Yeah.
and drop it in ice water, how long it takes to?
You want to put the ice one?
Yeah, I mean, honestly, I think it's reasonably fast based on this. So you see from here down to where it's getting down towards pretty close to equilibrating with that temperature. I mean, that's maybe 2.5, 3 minutes. I think part of that also is just the amount of epoxy we put on the thing reduced the surface area of the aluminum. And if you've got more aluminum surface area, I ran a little model, it goes a lot faster, and as you reduce that surface area, then it slows down a little bit. There's definitely a lag time towards the actual sensor itself. It basically, you hit sort of something where it's sort of asymptotes towards what the actual temperature of what you're fluxing it is. But it takes a while to actually get there. So I'd say, maybe a couple of minutes, maybe even a little less than that. For if it's built with a little less epoxy, it's a little clearer. How long it actually takes to get to like the true temperature, we haven't calibrated to that yet.
You want to go to the car?
Sure.
Yeah. So here, in terms of reactiveness, as soon as you put in the cardboard shade, things immediately drop.
Yeah.
So in terms of reactiveness, it's pretty much instantaneous. In terms of equilibrating, if you want to go to the calibration plot, when changing from big temperatures to get an exact reading, it can take, I should have put this in minutes. It can take a while.
Also, I'll add to that. This test was done in the temperature chamber where largely it was coupling with the temperature of the air, which is a lot less conductive than like water or ground. And so you can see on here, it would take, up to 10 minutes or even, I don't know, we left some of them going a little longer.
And then the other problem was that we didn't isolate it from the floor of the temperature chamber. So there was a lot of contact with that. So as long as the temperature chamber wasn't equilibrated, there would still be variations in our sensors as well.
And I'm just going to point out on here, I think this shows that it was actually pretty fast because it wasn't fully submerged. Just the process that we had of trying to get this thing to sit in the ice and in the ice water, it wasn't fully submerged in 0 degree water at the beginning, and you can see how steep that slope is around minute 2. So I think that is a good sign that in water or in more thermally conductive materials, it would equilibrate pretty fast.
What's up, Otis?
The question about the design of the metal. What kind of metal is it? I missed that.
Aluminum.
Jinx. Were you trying to center the sensor in the center of the puck? I don't understand why there's 2 holes.
Yeah, so the reason for the 2 holes is not actually about anything in particular we wanted to do with the sensor. It's about the wiring. So we wanted to be able to feed the wiring in because of the fact that you need to have this, if you want to keep it relatively manageable, you want to keep the same ground wire, you want to keep the same data line, not data line, the same power wire. So you want to pass those through each. And for us, the easiest way we found to do that was to drill a little hole in there so that we could pass that sensor into that hole, have it in contact with the metal, and then pass those wires into the hole after we'd soldered them with the sensor. So basically the idea being, and it didn't quite work with this because it was a little too big, but the idea being something like we've got that little hole, we're passing this through, and then we can stick that in there. This is the puck, and then epoxy that in. It's not actually about anything inherent in the system, it's about wire management.
So initially, we knew we needed to epoxy the sensor in the pot, and we were like, cool, then we'll have 4 areas of epoxy within our thing, because our only exposed wires are going to be right around that. It didn't turn out that way. We have a lot of epoxy everywhere in our wires, but initially the goal down was that all the wires could be in there, and it gave us like a big volume of where to put the epoxy. So we don't have to do like a rotisserie chicken of trying to pour epoxy and cure it all around the wires without the mold. Doing this again, we would make mold for epoxy doing, because pieces of tape don't do well.
And also just to emphasize, the hole didn't need to be through going. What it was a chamber for that sensor. It's just a lot easier to machine it from the outside in than from the inside out.
So you have your aluminum block, which makes sense because that's usually nothing. But then your chamber there, that little hole that has your sensor in it, is full of epoxy. The epoxy isn't very conductive.
So the idea is that the sensor, we have a pretty small diameter hole here, and because of just the tensions in the wires, the temperature sensor is in direct contact with the aluminum for all of them. Like we can verify that visually, and so even if on one side it might be epoxy, it is still in contact with that metal.
So we tried to have the tightest fit between the sensor and the hole, and it was like hard to watch, like because we did all the wiring first, and then putting the sensor in, it was a very tight fit. And then we did our best to put the sensor flat onto the metal area before we epoxied it, and I think the variations of how well we're able to do that kind of played into why we did different calibration for each of our sensors, because there might have been really differences.
And also there's just trade-offs there. Like obviously if we weren't using any epoxy and there was no epoxy and the entire thing was more in contact with the aluminum, it would heat up faster, but then it wouldn't be waterproof. And we wanted this to be something we could use in some environments that were not necessarily easy. So for us, that was a worthwhile trade-off to have something that maybe, still heats up relatively quickly, but maybe not as quickly as it could, but we can use anywhere.
And the epoxy is better than air.
Yeah.
All right, thanks.